Okay, Jason, we're ready to go.
Great. So is there someone who has to introduce me, or do I have to do that myself?
Nope, you do that yourself.
Excellent. Okay. Hi, everybody. I'm Jason.
Hi, Jason.
Coming to you from the future, obviously. Bridge of the Enterprise, NCC 1701-D. Also from Edmonton, Alberta, where it's actually still morning, and we're not having any thunderstorms, so I don't get to join in on that, but that's okay. Let me bring up my slides here. I am here to talk today about Rules as Code, and I am the Director of Rules as Code at the Public Health Agency of Canada. I'm also the CEO of Lexpedite Legal Technology. And a little bit about my background. I started out as a database analyst and software developer, went back to school, became a lawyer, ran my own practice for 7 or 8 years, and then did a master's degree in computational law at the Faculty of Law and Department of Computing Science, interdisciplinary at the University of Alberta. While I was doing that, I also taught a couple of courses at the U of A Law School called Coding the Law. And then I started working for SMU, Center for Computational Law, as a researcher. And then after that, I started working for the federal government of Canada in Employment and Social Development Canada, and now in Public Health Agency of Canada as the Director of Rules as Code. And so that's my CV, as it were. The plan for the presentation today is I'm going to start describing a little bit about what the vision of Rules as Code is. And then I'm going to talk about how close we actually are to that vision and how much further we have to go. And then I'm going to give you a demo of a piece of software that I've been working on pretty much full-time for the last couple of years called Blawx, which is designed to kind of illustrate what the future tools of Rules as Code might look like. And my hope is to leave lots of time at the end of the presentation so that either we can have questions and maybe even answers, or if there are no questions, then you guys can get a little extra time to dry out your clothes or whatever you need to do after the thunderstorm. Okay, so phase 1, what is Rules as Code? What I'm going to do here is I'm going to tell you some stories. And I'm hoping that these are going to give you a kind of a contextual background that will make the definition of Rules as Code make more sense. Okay, so 4 stories. Story number 1, in New Zealand, they have a law called the Holiday Pay Act, which does pretty much what you'd expect it to do. It was badly drafted. Specifically, they failed to sufficiently define the phrase work week, which turned out to be very important. So what happened is a lot of HR software companies needed to implement the Holiday Pay Act in their code so that people, including the New Zealand government, could calculate paychecks and pay people. And because work week was ill-defined, essentially these software developers had to make a guess. You would hope that they were legally advised as to what this guess was, but maybe not surprisingly, they also made the guess that would result in their clients having to pay the least. And so all of this software was being used by organizations all around New Zealand, including the New Zealand government, to calculate paychecks. And then in 2018, the courts in New Zealand said, wrong guess. That wasn't it. It was the other thing. And what happened was billions and billions of dollars in overdue holiday pay payments, including from the government to its own employees. But this was not a problem limited to the government. This was basically everyone in New Zealand was owed money from their employer for holiday pay. A huge problem. This news article on the screen here is from this year, which is 5 years after this problem became, everyone became aware of the problem. And the government of New Zealand is still $2.1 billion behind in the amount of money that they're supposed to be paying their employees. So how did this happen? Well, when the law was being drafted, the people in the room didn't realize that work week was ill-defined, and they didn't realize that it was important. And so they didn't realize it could have these massive implications, and they didn't fix it. What's noteworthy is that all of the people who were writing software for HR software companies, those people did know that this was a problem. And had they been in the room while the drafting was happening, this entire schlemazel could have been avoided, but they weren't in the room. That's story number one. Story number two, and this is a happier story. This is policyengine.org. This is a website that you can go to and make proposed changes to US tax and benefit policy and analyze those changes. So yesterday, I went to the site and I created a proposed policy, policy number 14940, evidently. And I just randomly picked two policies and abolished them. Just got rid of two programs and then asked it to show me the relative impact of that change on people by income decile. And what you see on the screen here is the result of that analysis. So that in and of itself is super cool. What's kind of astonishing is that this took me 30 seconds and I didn't even need to log in. So abolishment is only one of an enormous number of things that you can manipulate inside this tool. You can change income thresholds, you can change tax rates, interest rates, allowances, durations, ages, all kinds of things. And whatever you do, it will take your changes to the rules and then apply it to a statistical database kind of sampling of the US population in order to show you how those policy changes would actually impact people, the distributive effects of those changes. How is this possible that I can do this in 30 seconds? It's because of an open source library for the Python programming language called OpenFisca. The policy engine people created their own version of OpenFisca, and they're using it to encode a growing variety of US tax and benefit policies. And they're doing similar work in Canada, and they have done a lot of similar work in the United Kingdom. And all of their encodings are open source, along with the software that powers the website. So if you want to run your own version of Policy Engine, you can. Just take it and do it. So that's another example of encoding rules. Third story. When I worked at Singapore Management University, we did an experiment. We encoded a part of the professional rules governing the legal profession in Singapore. In my jurisdiction in Alberta, these are usually rules of the Law Society. In the United States, I think it's the courts are involved. I'm not really clear. In Singapore, it's actually like a government law. And so when we did this, we did some testing on our encoding, and we discovered a drafting error that we didn't know was there when we started. So we discovered the problem when some of our tests started to give us unexpected answers. And what we were checking was whether or not it was allowed for lawyers to accept positions in corporations. And there were a bunch of complicated rules about when this is okay and when it's not. And we had this test and we were expecting the answer to be, no, you can't do that. And it said, no, that's fine. And we said, wait, why? And the software was able to explain to us with something to the effect of, the company engages in the sale of pottery, and the sale of pottery doesn't interfere with the lawyer's ability to serve their clients. And that, if that sounds like gibberish to you, it's because it's gibberish. It doesn't mean anything. What we had said was that the job would interfere with the lawyer's ability to serve their clients. And we thought that that was going to trigger a no. But what the software was checking was whether or not the category of business interfered with ability to serve the clients, which again, doesn't mean anything. They're words that you can string them together, but they don't have any actual, they don't represent anything in the real world. So we were curious, why is it saying that? And of course, this is software. It said that because we told it to. But we saw the code, and that's exactly what we told the code to do. So then we're like, why did we tell the code to do that if that doesn't mean anything? And so we looked at the law. And when we looked at the law, we saw the problem. The law in that section used the word business. And the word business had been defined in the Act elsewhere. But in that section, they weren't using it to mean the definition of business, which was something like area of business, like an category of undertaking. They were using it in that section to mean something more like job. They were using it in a colloquial sense. And that was the reason. That was the reason that we had coded it that way. We had assumed when they said business, they meant the same thing that they always meant when they said business. And that was the reason the test broke. And somehow when we read the law, we didn't notice this. And when we encoded the law, we didn't notice this. We only noticed this when we tested the law. And so we were able to use this programming language to debug a piece of legislation. Fourth story, last one. The world is getting smaller. If you offer services on the internet, you're offering services everywhere. And that means you need to comply with everyone's regulatory requirements. If you've been on a website recently, you've clicked on one of these annoying "is the cookies okay" thing, which is probably there first because of legislation out of the EU. And the rate of regulatory change has been accelerating with time. So in a connected world, the need for compliance is growing, but the complexity of compliance is growing exponentially. As one example of that, it's estimated that the average bank currently spends $10,000 US each year per employee in order to maintain compliance with the changing rules that they're obliged to comply with. So when the rules change, or as is frequently the case, when the rules are added to by some other jurisdiction, each bank has to implement the changes in each of their existing systems. And when the compliance can't be totally automated, policies are written, and then every employee needs to learn how to follow the new policies, which is part of the reason that this cost scales by employee. The costs are enormous and growing, and the work of implementing the new rules is duplicated over and over again in multiple different banks at the same time. So that's our 4 stories, okay? What do all of these stories have in common with each other? They all involve rules, and they all involve automated systems. And there are advantages when the rules and the automated systems fit together well. And there are disadvantages, and sometimes severe disadvantages, when they don't fit together well. So that gives rise to the main insight behind rules as code, which is this: encode the rules using interdisciplinary expertise in an authoritative and trustworthy way as soon as possible, and then share and reuse those encodings as widely as possible. So this is the advice that rules as code offers, right? And why does this help? It helps because if there are problems in the automating of the implementation of the rules, you will discover and be able to correct those problems early. And that will minimize costs. And also the problems may not be just with automation, they may be with the rules themselves. So you may end up with better rules as a result of following this advice. And on the other hand, if there are advantages to having encoded the rules, and there probably will be, you will capture those advantages early, which maximizes the benefit. Because if you have the encoding and the encoding is trustworthy and authoritative and it already works, then you can just share it. And maybe each regulated entity doesn't need to rewrite their own software. Maybe each department of the government doesn't need to rewrite their own tools. Maybe each branch inside your department doesn't need to rewrite its own software tools. So that's the basic idea behind rules as code, which I think gives you enough background to be able to understand the definition, which is rules as code is a methodology of public administration that calls for rules to be digitized as early as possible by interdisciplinary teams in machine executable languages to improve policy design, legislative drafting, service delivery, and compliance. So how can we govern better if computers understand the rules? Okay, that's phase 1. Congratulations, you've all graduated from Rules as Code 101. So let's move on to Rules as Code 102. How close are we to this vision of Rules as Code? There's good news and bad news. We are doing a lot of work and we're learning fast, but we're not there yet. And the problem is the tools. So this work began in earnest about 10 years ago in New Zealand. And you may think it's a coincidence that the holiday pay thing happened in New Zealand and Rules as Code started in New Zealand. I don't think that's a coincidence. But they kind of started it, and it's been spreading primarily through Commonwealth countries, actually. So Australia, Canada, the United Kingdom. But it has also joined up with similar related projects that are underway in places like France and Finland. and many, many others. Canada, which is where my expertise is, Canada has been looking at this for about 5 years, and I've been helping them with it for about the last 2. And the OECD recently identified rules as code as one of the most important innovations underway in the public sector. So there is a lot of growing interest in rules as code, and there's a lot of places around the world that are kind of doing experiments, trying it in order to see what happens. Very, very kind of early design stage development. I can say inside the government of Canada, it also seems clear to me that we are getting requests for help with rules as code experiments. We're getting more of them, and we're getting them more frequently. So it seems to be growing exponentially inside the government of Canada, but also outside. That said, what we're doing isn't, what we would love to be doing. There's growing interest, but the work is very piecemeal. We're kind of playing around the edges of it, experimenting with small parts. The tools are still under development, and that's a big deal because you can't have processes without tools. So every time the tools change, the processes have to change too. So everything is kind of still very much in flux as we navigate through what's good and what's bad and for what. Most of the tools that are out there are programming languages, which is a problem I'll talk more about in a second. The tools are not very reusable. So the software that Policy Engine is built off of is great if what you are is a Python programmer and what you want to do is economic microsimulation. If what you are is a legislative drafter and what you want to do is debug legislation, OpenFisca is not really the right tool for you. So we don't have the reusability that we would really like to see yet. And the fact that these tools are programming languages interferes with our ability to collaborate in a multidisciplinary way, or excuse me, an interdisciplinary way. So this is my extremely opinionated and therefore potentially wrong list of things that we need out of a tool for a kind of ideal rules as code tool. And the motivation here is that we want people from different disciplines to be able to work together and share knowledge and experience and wisdom and all be working on the same artifact, right? So they're all dealing with the same object and reading and writing and manipulating and validating the same thing so that communication is very efficient between them. That typically is not how this goes. Typically, the way that it goes is you've got programmers in the room, you've got lawyers in the room, and they talk to each other and try to understand each other. And then the programmer goes off and implements what they thought they understood, and then they have the lawyer test it. And that's kind of how we try to figure out whether or not the communication worked. In my mind, what we need is something where when the programmer writes the encoding of the law, the lawyer can just read it and say, yeah, that's right. Or at least look at it and test it themselves with their own knowledge and experience in order to validate that it's correct. So we need something where lots of different people can read it, write it, use it, and validate it. And we have to say that, because this is a public sector thing, if it's not open source, it just won't get used. The trend in public sector is away from paying Microsoft and Oracle incredible amounts of money to be locked into software that doesn't do what they need it to do, and then they're unable to change away. There's a very strong trend towards the use of open source, cloud-based software, standards, and all kinds of things that give them the flexibility to change when they want to. So it also needs to be open source for it to be realistic to be used, and it needs to be easy to integrate with other tools. So that's what we need from what I call Spreadsheets for Law. Why do I call it Spreadsheets for Law? So this is VisiCalc. VisiCalc is the very first spreadsheet software. In fact, it is the very first killer app. The invention of VisiCalc is the reason that the PC revolution started when it did, because there was a piece of software that people wanted enough to justify buying personal computers. So this was created in the 1970s. And in the 1970s, I want you to imagine that you're an accountant in the early 1970s before VisiCalc comes out, right? If I ask you if you're using computers in your practice, the answer is almost guaranteed to be no. And why not? Well, it wasn't that computers were incapable of doing math. Computers are great at math. And in the early 1970s, we had programming languages specifically for getting computers to do math. So the technical capability was there. The problem wasn't getting computers to do math. The problem was getting accountants to do computers. And the problem there was not with the accountants. The problem was with the computers. The interface to getting a computer to do something for you was a programming language. And programming languages are a bad interface. The reason they're a bad interface is because you can't see by looking at one how difficult it's going to be to learn how to use and what value you're going to get out of it. And so you have no incentive to try, right? It looks hard and you don't know what you're going to get, so you don't bother. And so people didn't use programming languages for math until VisiCalc. And VisiCalc solved the problem by turning by turning the task of getting computers to do math into an application. And I'll tell you a secret. From my perspective, spreadsheets are not just an application. Spreadsheets are a declarative, domain-specific programming language for math and finance with a friendly user interface. And I'm right about that, but people who use spreadsheets don't know that, and they do not care. And they shouldn't, because spreadsheets are helpful and they are easy to use, easy to learn. And so they are worth learning to use. And that's why they get adopted. You can look at it and see that it is useful. You can see that it will be easy to learn. And so you are motivated to do it. So that's what drove the adoption of spreadsheets as opposed to just programming. That's what drove the adoption of personal computing. So this is the question that's in my mind, is what would happen if we had a declarative domain-specific programming language for legal reasoning with a friendly user interface where people could do programming and they didn't know or care that they were doing programming because it was easy to use and it was helpful. And so it was worth learning, right? What would happen to the legal profession if that tool existed the way that spreadsheets now exist for accountants? And that's the question that I've been obsessed with more or less since 2016, when the area of declarative logic programming was introduced to me by David Colarusso, who I think you may have seen his presentation earlier today. So thanks, Dave. And as a result of being obsessed with that question, I have built Blawx. So that is my attempt at an answer, and I'm going to share it with you now. Let me just do the fancy video thing. Whoosh, awesome. Okay, demo time. And I'm demoing this off the live server, which you should never do. I don't recommend it, but hey, let's live a little. So this is Blawx, and I'm going to start by creating a demo project here called the Rock, Paper, Scissors Act. Most programming languages, you start with Hello World. For rules as code, I start with rock, paper, scissors. So the way Blawx works is that you have a rule editor and a code editor. And in the rule editor, you start by giving the name of the act and then the text of the act. I've created a markdown-like syntax where you just type it into this little text field here, and you have to follow some rules in order to get it to work. I don't like this interface. This is prototype software. I'm currently working on replacing this with something that's a lot more like, like Google Docs or Word, where you can see the formatting as you're going. So this will improve, but the basic idea is you start by putting the law in. The law is the structure of everything that you're doing with the code. So once you have the law in there, you go into your code editor, and you can see that the scaffolding of the law has become the scaffolding of your code. So all of the sections and subsections are available up here, and you can click on one in order to see the code that you've created to represent just that section. This is convenient. That's one advantage of it, but this actually turns out to be really important, this one-to-one relationship between sections of law and sections of code. One of the reasons that it's important is because if you have that one-to-one relationship, then the code knows exactly what section of law it was written to represent, and it can use that information when it is explaining its answers, which is very helpful for explanation. And if the software can't explain itself, It's not going to abide by all of the, the rules that are coming out, the automated decision-making regulations that are coming out about appealability and explainability and all these things. It needs to be very transparent. And so explainability is core, and having that one-to-one relationship helps a lot. Another thing that helps is that it kind of breaks the work of encoding down into pieces, so you know exactly which sections are finished and which aren't. You never have to worry that when you read a later section, you're going to have to change something earlier in the code. So that is helpful for writing. It's also helpful for validating, because you can actually divide up the task of validating the code by section. And one person can validate one section, and another person can validate another. And you don't need to worry that they each need to be looking at what the other person looked at. But most importantly, the rules change. And if you have this one-to-one relationship between the text of the law and the encoding, then when the rules change, you know exactly what sections of code need to be updated. And that is actually a huge improvement in terms of what it's possible to do with encodings of legislation going forward, because maintainability of systems that are built to comply with laws is currently a huge issue, along with being able to validate the legal quality of them. So the code, what are we actually doing here in this window? We've got Blawx. You will be familiar with this kind of interface if you are relatively young, or if you have children who have learned programming in school. The library that's used to kind of create this drag and drop interface is called Blockly, and it's open source and published by Google. It is evolved from the source code that was used to build Scratch and a bunch of other tools that are out there for teaching kids to program. We're not teaching kids to program. This is an example of one of those situations where when you make something more accessible for anyone, you make it more accessible for everyone. So it turns out not only is this a good way to teach programming, this is just a better way to do programming. Some of the advantages that come from this visual drag and drop interface are that there's all kinds of syntax errors that it's now impossible to make, because the blocks won't go where they don't belong. They just won't fit. You can see right away that it doesn't belong there. And the other advantage is that programming languages are designed to minimize the amount of typing required. And that makes sense if you're going to be typing it. But what that means is that the programming languages are very condensed, and there's a lot of symbols, and there's not a lot of explanation of what's going on inside the code. Here, it doesn't matter how much text is on the block. It takes me as long to drag that block as it takes me to drag that block. So there is no design disincentive for me to include a lot more language here and make this something that's more legible and makes more sense to the people who are reviewing it, who may not be familiar with like computer programming syntaxes. So those are some of the reasons that we're doing the visual interface. So now what do you actually do, right? The actual task of encoding in Blawx is two parts. The first part is you give it the vocabulary, and then you interpret the rules. You translate the rules into the Blawx language. So here in section 1, we're saying a game of rock, paper, scissors has 2 players, and Blawx knows about nothing at this point. So we have to explain that games are things, we have to explain that players are things, and we have to explain that games have players. And as we're doing this, we're explaining to Blawx how to display this concept to the user, right? So here you can see it says object is a game, which is the reason that I can now go in here and I have blank as a game. And here it says blank played in blank. So player played in game is the definition here, which is the reason that under here I have blank played in blank. So as you define these terms, it's generating a visual block language for you based on the terms that you gave it, right? So that's the first step. First step is give it the vocabulary. And then the second step is give it the rules or the facts. Here, there's no rules or facts we need to worry about. Section 2, there are 3 signs. So all we're going to do is explain that sign is a category. Section 2A, we know rock is a sign, right? So now we've used the category that we defined as sign, and we've got this nice little block here. We've said rock is a sign, and now that's going to show up in known objects. So we can fill that into other blanks somewhere else in our code. We do the same for paper and for scissors, and then signs are related to each other. And so we create the attribute beats, where one sign beats another sign. And then we say rock beats scissors, scissors beats paper, and paper beats rock. Or sorry, yeah, paper beats rock. Oh, that's not in the right section, is it? That's interesting. I never noticed that before. Those are reversed. This one's right. Rock beats scissors. And you can see that's very clear, right? If you ask someone, hey, you're an expert in the Rock, Paper, Scissors Act, would you please read section 3A and verify that this code is correct? That's a realistic task to give a non-programmer. And that's what we're aiming at here. And then we've just defined facts up here. Now we're going to define a rule. So the winner of a game is the player who throws the sign that beats the sign of the other player. So we need to say, what is a winner? We're going to say games have winners, and they are players. And then we're going to create something called a relationship between a player and a sign and a game called throw. And that should be displayed as player through sign in game. And because we've defined those things, we now have a winner block available here, and we have a throw block available here that we can use to actually create the rules. So that language has been created. Now we just need to encode the actual rule. And this is what that looks like. So this is as natural language-y as I can get it, because the idea is to make this approachable for people who aren't familiar with the code. But we still have to be aware of the semantics of the programming language, and there's still some skill involved in understanding what needs to be explained and what doesn't need to be explained. So here we need to say if there is a game, and if there are two players, and they are not the same thing, they're not the same entity, and they both played in the game, and they threw things that we're going to call throw one and throw two, and throw one beats throw two, then we know that according to the Rock, Paper, Scissors Act, Section 4, the winner of the game is player one. So this is how we have formalized the rule in the declarative language. And when I say it's a declarative language, what I mean is this is not, as in most programming languages, a set of instructions to follow about how to manipulate data or how to manipulate variable values or make function calls or things like that. This is not a series of instructions. It's a literal translation of the implication in the rule. And so that is designed that way because rules are written with implications. And if our code is also written with implications, then it will be easier to translate from one to the other, and we will lose less in the translation and have less risk in that translation. And it's going to be easier for people who are experts in the rule to understand whether or not the code represents that rule accurately. Just in case you're interested, the programming language that's being generated when you do this is called SCASP, and you can actually see the SCASP code that's being generated based on your encoding. And this is the rule part. So this is a very Prolog-like programming language that we're using, but this is what you're actually generating when you write that code. Okay, so we've got our law, and we've translated our law into this language. We had to build up the vocabulary and then make a bunch of statements about what we know and what the implications available are. But this isn't software that does anything yet. So how do we get it to do something? Well, you have to ask it questions. Give it facts and ask it questions. So the way you do that in Blawx is by creating tests. You can go in here, and we're going to create a game called Test Game, and Bob and Jane are players, and they both played in the test game, and Jane threw rock and Bob threw scissors, and then we're going to ask a question. The winner of Test Game is who, right? This is a variable, so we're asking fill in that variable with any answer for which the variable would be true, kind of like algebra. And if we run this test, it's going to calculate the winner, and it's going to give us an explanation for why they are the winner. This version is a tree structured explanation, and you can see it follows the rules. So you're getting an answer and you're getting an explanation, and that explanation is linked back to the text of the law from which the encoding was derived. So you've got clear accountability for your automated system back to the law that it was supposed to implement. If there's more than one correct answer, it will give you all of the correct answers. And if any of the correct answers have more than one reason that they are correct, it will give you all of the reasons that they are correct. So when you are examining this, you can use this not only to figure out if your software is giving you the right answer, but you can use it to figure out if your software is giving you only the right answer, and it's giving you only the right answers and only for the right reasons, which is a degree of insight and quality assurance for legal software that isn't available really with any other technique available today. And it's not able to deal just with facts. It's also able to deal with the absence of facts. So let's imagine I've encoded the rules of rock, paper, scissors, and what I would like to know is, what are the possible ways that a person could win a game? Show me all of the possibilities. And then from that, I will figure out whether or not the software is reasoning correctly about the rules. So here I'm saying, assume that there are games, create Bob and Jane as players, assume that people play in games, assume that people threw signs in games. All of these are uncertainties that you can make assumptions about in order to find an answer to this question: is there a game that Bob won? And when we run this code, it is able to use hypothetical reasoning, which is technically abductive reasoning, to find 3 answers. And I think you can probably predict how the 3 answers differ. One is rock beats scissors, another is scissors beats paper, and another is paper beats rock. So the fact that it got those 3 answers for those 3 reasons tells me a lot about whether or not it understands the rules the way I understand the rules. And that, again, is a feature that's not available in most software systems that are currently available. And you get all of these advanced reasoning capabilities in a programming language that is supposed to be friendly to use. So that's a huge advantage. And then this is great if you're just testing the software and you're validating it and you want to, see if it does what you want it to do. What happens when you want to actually use the software for something? Well, all of the tests are exposed as an API, which means it's a piece of software that you can connect to over the internet and ask it questions and get answers back in order to build your user interface, do whatever you want. And this is Scenario Editor, which uses that API in order to ask questions and get answers. So this is actually the wrong test. Let's go back and just who wins. So our test here is, who is the winner of what game? And then if we go into the Scenario Editor, we've got this friendly user interface where we can create some facts. So I'm going to make a game that me and David played in, CaliCon test. And let's add me as a player. And let's add David as a player. And this is the interface that your subject matter experts would be using in order to create different fact scenarios and see if your encoding is behaving the way that they expect it to behave. So change things as you need to in order to see whether or not it responds correctly. So we're going to make David throw paper because David's smarter than I am. And then we're going to run that. And it's going to calculate that David won the game. And it's going to explain that to me. And the explanation here is formatted a little differently. Instead of a tree, it's a series of linked paragraphs. But it uses the same content, and it's still linked back to the source material. You can click on section 4 and see what the actual text of section 4 is. So this is an example of, you've encoded it, you've created a test, you've exposed your test as an API, and now any other piece of software that can connect to your server can create legal fact scenarios and calculate the answers in those legal fact scenarios and get the results back in an authoritative and trustworthy and validated way, because the code was validated by someone who actually understood the rules. So that's kind of what we're aiming at. That's how far we've gotten so far. I'm gonna, I gotta click on my fancy thing here. Go back to the slides. And we've got a little bit of time maybe for some questions. So let's do that.
Was a question in the chat where someone asked if they were hearing Coda's law conceptually is the same as symbolic logic.
So it's a good question. The correct answer is no, but the caveat is that is true when you're talking about Blawx specifically. rules as code can be used using, can be accomplished using any kind of technology. Predominantly it is done using programming languages like Python or what have you, just whatever the person was familiar with when they decided to take on a rules as code project. Blawx is specifically aimed at a logic programming approach, and it's aimed that way because rules are written in a semantics that is more similar to formal logic than it is to procedural logic or lambda calculus inside a functional programming language. So I think it's a better starting place. If you're asking me whether I think rules as code ought to be done using a fundamentally symbolic logic approach, I think the answer is yes. But I'm in the minority in that regard. So you've caught on me as a symbolic logic advocate, but it's not necessarily everyone who sees it that way or does it that way. Any other questions? I see Canada is not quite yet at 40 million, so that'll have to be for your next session. Okay, well, I think that we're at time, so I'm gonna wrap up there. Let me say that I am Jason at lexpedite.ca, and if you are in a law school and you think that your students or your staff would be interested in learning about this, I would be absolutely delighted to have the opportunity to talk with them about it. Please don't hesitate to get in touch with me. And yeah, and thank you very much for the opportunity to join you today. This has been a lot of fun, and enjoy the rest of your Friday.
Okay, so I'm going to stop recording and it'll end the webinar, and then the video will be up on YouTube in the next week or so.
Sounds great.
Okay.
Thanks very much.
Thanks, Jason.